Okay, so today we're going to be talking about moles and concepts related to the mole before we get into ideal gases in the next video. Before we do that, just take a look at this quick warm-up question. This question says, state two ways in which a real gas differs from an ideal gas. Okay, and so using what we talked about in the last video, see if you can answer that question in complete, coherent sentences. Pause it here if you need to think about that and refer back to your notes, and then we'll see what I put on the next slide. Okay, so there's a few different ways to answer this question. Here's what I wrote, and this is, again, not the end-all be-all answer, but it does answer the question. I wrote that ideal gas particles do not have electrical forces between them and therefore do not have any internal potential energy. Real gas particles do have these forces and so do possess internal potential energy. Okay, that is one of the key characteristics of an ideal gas and how it differs from real gas. The second thing I put is ideal gas particles experience elastic collisions with each other. Real gas particles can collide inelastically. Now remember in the last unit, an inelastic collision is a collision where kinetic energy is lost in the course of the collision. Okay, and so in an ideal gas particle, we assume that the gas particles collide elastically, meaning that no kinetic energy is lost. Kinetic energy is conserved in those collisions, and that's not the case with a real gas. Now, there's other ways to answer this question, but that's just what I came up with. Now, make sure that when you answer this question, you don't make the mistake of answering the question that's not being asked. Okay, this question is not asking about the conditions under which a real gas can be treated as an ideal gas. Okay, now the answer to that question would have to do with things like, low pressure, low density, moderate temperature, high volume, stuff like that. Those have to do with in what situations or under what circumstances can you approximate a real gas as an ideal gas. That's not what this question is asking. Okay, so make sure you understand the difference between those two questions. Now, what we're going to talk about today is going to lead into doing calculations with ideal gases. It's actually a concept that you should be somewhat familiar with from chemistry, and that is the concept of the mole and molar mass, which I know is everybody's absolute favorite topic. In fact, you've probably repressed some of the stuff from chemistry from last year. So pause it here if you need to take notes. Now here's what it says in the notes. It says, before discussing the ideal gas law, it is beneficial to discuss the concept of the mole and molar mass. Now, definitions are important. Here I have the definition of the mole. Now, it is important that you know the definition of the mole. Again, definitions are important. And it says that 1 mole, by the way, the mole is one of the 7 SI base units. Remember, you've got the candela, the Kelvin, the ampere, the meter, second, kilogram, stuff like that. And so it is one of the 7 SI base units, and so it is kind of important. And it's defined as the amount of any substance that contains as many elementary entities as there are atoms in 12 grams of pure carbon-12. Okay, so again, pause if you haven't added this to your notes yet. Now, the first thing I need to point out that's really important, this is a big misunderstanding of what the mole is based off of the definition, the mole is something that measures amount. Okay, so the SI unit for length is the meter. The second is the SI unit for time. The mole is the SI unit for amount. Okay, so the mole I think of as a counting number. Okay, for example, this is the analogy I love to make. Dozen is a counting number. If you say buy a dozen roses or give me a dozen donut holes, everybody knows what that means, right? Dozen means 12. Okay, mole is used in the exact same way. Okay, it is a counting number. It refers to a specific amount. Now, what amount is that? Well, it is an amount that's equal to as many as many atoms in 12 grams of pure carbon-12. Okay, and so just like we have dozen meaning 12, 1 mole of something just means you have as many atoms as there are in 12 grams of pure carbon-12. Now, of course, we need to know what that value is, right? And so what is the analogy here? Dozen is to 12 as mole is to what? Well, that number has a name and it has a value. The name we give that number is Avogadro's number. It is typically written as NA if you ever see it in an equation. Okay, N for number and A for Avogadro's number. And the value of that number is a number that you've probably seen before. Okay, the value of Avogadro's number is the number of atoms there are in 12 grams of pure carbon-12, and that is approximately 6.02 times 10 to the 23. Okay, and so that is Avogadro's number. That is how many atoms there are in 12 grams of pure carbon-12. That's just, again, how the mole is defined. It is defined as, this number, which happens to be equal to how many atoms there are in 12 grams of pure carbon-12, and based off of the measurements that we've done in many experiments over the past couple hundred years, this is the closest approximation that we can get. Well, we can probably get more precise, but for the purpose of the high school class, 6.02 times 10 to the 23 works fine. So dozen is to 12 as mole is to 6.02 times 10 to the 23. Now, a lot of people get confused because they think mole has something to do with molecules, which I guess is kind of understandable because if you write out molecules, they have the same first 4 letters, right? A mole has nothing to do with a molecule. A molecule is a combination of atoms. Okay, a mole is a counting number. It represents a specified amount, just like a dozen represents a specified amount. Okay, it's just a quantity. If I tell you to buy me a dozen donuts, I want you to go get me 12 donuts. If I want you to get me a mole of donuts, that would be 6.02 times 10 to the 23 donuts. Okay, so 1 mole of donuts, just for example, would be equal to 6.02 times 10 to the 23 donuts. Okay, so it's important that you understand that the mole is just a counting number. It represents a specified amount. That's a 23, by the way, in case you can't read that. Okay, 6.02 times 10 to the 23. Okay, so make sure you understand that the mole is just a quantity. It's a counting number. It has nothing to do with atoms or molecules. The only reason it's typically applied in this unit is because there's so many atoms and molecules in given samples of things. Okay, so if we have times 10 to the 30 atoms, we don't want to have to keep writing times 10 to the 30, so we like to write in terms of moles. It just makes things a little bit easier to deal with. Okay, so make sure you add all of that into your notes and that you understand that the mole is a quantity number, it's a counting number, it has nothing to do with atoms or molecules. It just so happens we're going to apply it in that context. Okay, so 1 mole of anything has Avogadro's number of that something. Okay, so I'm going to erase this. We're going to go to the next slide, do an example. Okay, example 1. It says an aqueous solution contains 0.25 moles of iron. Calculate the number of iron atoms present in the solution. Okay, so this is a pretty basic calculation. We have 0.25 moles. The abbreviation for moles, by the way, is MOL. It's not a very good abbreviation because it's only short by like 1 letter. So I'm just going to write out the whole thing, moles of iron. And basically all these problems are going to be just simple unit conversion problems. Okay, so 0.25 moles of iron. If I want to go to the number of iron atoms present, like any unit conversion, I start with what I'm given. Then I arrange things so that all of the units cancel except what I'm ending up with. Okay, so if I have moles of iron on the top, that's Fe, by the way, for iron. Then I have to have moles of iron on the bottom, and the conversion factor is that 1 mole of iron has 6.02 times 10 to the 23 atoms of iron. Now, how do I know that? Because 1 mole of anything is equal to that quantity. Okay, just like if I have a dozen roses or a dozen donuts, it doesn't really matter what I'm talking about, right? Dozen means 12. Okay, so 1 mole of anything is about 6.02 times 10 to the 23 of that something. So in this case, 1 mole, I don't know why I put moles of iron, 1 moles 6.02 times 10 to the 23 atoms of iron. And then this cancels, and then you would just type that into the calculator. Okay, and so like any unit conversion, you just multiply across the top and the bottom and divide. And the value you should get, okay, you can check on your own. I'm going to round, is 1.51 times 10 to the 23 atoms of iron. So just a very basic type of calculation. Okay, so pause it there if you need to. Okay, we're going to do some more examples really quickly. Before we do that, just a little background about why are we talking about moles. And the reason is 1 mole has a set number of elementary particles. And again, when we're dealing with real-world situations, we have so many of these atoms or so many of these molecules that rather than talk about like, oh, I have 10 to the 40 atoms, it makes it easier to talk in terms of moles, just because a mole is such a big value. And again, if you think of microscopic versus macroscopic viewpoint, if we think of the microscopic viewpoint as, you know, each individual atom like colliding with each other, bouncing off the container walls, and we have so many of them, that's a lot of atoms to follow around. Okay, whereas if we just say, oh, I have like 1 mole or 2 moles, we can very easily talk about how enormous groups of atoms or molecules behave. Now, one more thing before we do some more examples is the bottom bullet point just tells you what is meant by molar mass. Okay, so molar mass you can think of as a unit conversion factor. Okay, unit conversion factor. Okay, now 1 mole of anything has a set quantity, right? 1 mole of anything is approximately equal to 6.02 times 10 to the 23 of that anything, whatever that is. Okay, atoms, molecules, roses, donut holes, whatever. Okay. However, if you think in terms of atoms, not all atoms are equal. If you think of hydrogen versus helium, for example, a helium atom is bigger than a hydrogen atom, right? Because, well, it has more protons. That's the key difference between a helium atom and a hydrogen atom. Hydrogen has 1 proton. Helium has 2 protons, not to mention, you know, probably more neutrons as well. And so 1 mole of hydrogen and 1 mole of helium don't have the same mass. Now, they have the same number of atoms, right? Because a mole is a mole is a mole. And so 1 mole of hydrogen is the same number of atoms as 1 mole of helium, but they don't have the same mass because each helium atom is bigger. And so this is where the concept of molar mass comes in. Okay, the molar mass of an element is the mass, typically in grams or kilograms, that 1 mole of that element consists of. And so, again, 1 mole of hydrogen versus 1 mole of helium atoms, same number of atoms, but different masses. Okay, again, the helium is going to have more mass for the same number of atoms. Okay, and so what you would say is the molar mass of helium is more than the molar mass of hydrogen. Okay, and so molar mass just gives us a way to compare for this set quantity of the mole how different compounds or different elements or different molecules are weigh different amounts. Okay, so let's do some examples with that concept. Pause here if you need to take notes.